and today he'll be talking to us about the history and future directions of the methodological development of how transport system risk is managed. So let's give a warm welcome for Dr. Simon.
Thank you so much for the warm introduction. So I have to say that part of the motivation of this presentation is I just finished a book with Dominic Lord on safe mobility, and we invited authors from all around the globe to contribute to this text in this book. So it should be out beginning of 2018. And one of the chapters in there was a chapter about what I'm going to share with you today, which is really about the history and the evolution of transport safety management. But before I get into that, I want to tell you a little bit about the University of Queensland, because I've sort of been going around and talking to people to find out if anyone's been to Australia. And most people have said no. Most people have not been to Australia. But Queensland, so Brisbane is this picture on the right. That's a picture for one of our great viewpoints in the city. It may look like the ocean, but it's actually a river right through there. So Brisbane is a river city. We're about 10 kilometers from the ocean. And north or south of Brisbane, there are world-class beaches and about 10 miles in either direction. And UQ, this picture, and I told this to Mike earlier, so civil engineering enjoys, which is very unusual, the best building in the University of Queensland campus. So it was finished 2 years ago, and it is the envy of all of the rest of the campus. And this is actually the new building that civil engineering houses on the UQ campus. So enormous building, brand new 4-star energy building, just a little bit of a flavor of what civil engineering is at UQ. We have about 750 to 800 undergraduate students studying civil engineering at UQ. That's now gone up to 40 academic staff. So that's a little bit different in Australia. So we have lecturer, senior lecturer, associate professor, to professor are the levels of the academic staff in Australia. And then as you look down the list, we have about 115 to 120 PhD students studying with us in civil engineering. And we have 8 subdisciplines, as you see around in civil engineering. And one that I haven't had in any of the civil engineering programs I've been in is a fire safety engineering, which is very fascinating. We have a big fire lab. We do these massive fire experiments, set couches on fire and things like that, and that's research. I'm not exactly how that works. But and we have an amazingly diverse academic staff in our school. And this is sort of a list of where people are from on my academic staff, and I'm quite proud of that because we have 40 people in about 27 countries represented on our staff, so it's pretty exciting.
What's the official title? You're Associate Professor of Fire? Or full Professor of Fire?
Fire Safety Engineering. Yeah, you could shorten it to fire, I guess, but yeah, no. That's cool. It is actually very cool. All right. So this is a bit of an unusual presentation, I hope for you as well as for me in a good way. I'm going to tell a little bit of a story, and so one of the realizations I had over the last year or two, that and this happens as you go down your academic career a little bit, you've actually done enough work in a specific area that you can start to tell a story. So rather than here's one research project that I've done, and here's what we did, and here are the results, I'm going to tell you a little bit more of a story about the evolution of this entire subfield of transport, because I think we rarely get a chance to glimpse how the thinking has evolved in a subdiscipline. And so the thinking and how it's evolved in the academic community is very, very insightful to understand why we made decisions to go different ways and manage safety in a different way. What were the pivotal sort of lessons or underpinnings of those decisions? Because then, having the historical context, you can understand what decisions are being made now to move ahead. So I'm going to take you from the past and take you through an evolution of thinking in this transport safety management space to where we are currently, and then where I think we ought to go moving forward. And so what I won't discuss, so you see what I'm going to talk about in the talk, but what I'm not going to discuss, because it's a very big topic, I'm not going to talk about how we decide what to do to fix a site. I'm not going to talk about how we choose among countermeasures, how we would fix the location, and figure out cost and all that. So I'm not going to talk about how we fix sites. I'm going to talk about how we identify sites that might be improved, or that we think might need to be improved. And I'm not going to get much into the math statistics. It'll be a little bit. I'll talk through, but I'm not going to dive deep into equations. That's actually, I don't think, all that informative to do that. There are plenty of papers I can point to that will give you that. So I sacrificed a little bit of depth to give you the breadth of this discussion that has played out in the literature for about 30 years, and pivotal decisions that were made along the way. Why do we even care? Let me answer that. So you're probably all aware why we care about managing transport systems. And I only have one slide to sort of talk to you about that. But if you think about the transport systems that we currently have and manage right now, if I turned to you right now and said, your job is to invest public money to do the best job you possibly can to improve an entire city, the entire city of Berkeley, or the entire Bay Area, that's a tall order, that you are charged with spending public money to save the most lives and reduce the injuries and carnage on the roads. And if that's your task, it's a pretty tall order. If you combine that with what we think is happening and the trends that we project, that we think that road traffic accidents by 2020, now, depending what happens with driverless cars in 2020, could have a big impact on them. But let's ignore that for a second. The projections are that in 2020, road traffic accidents will be the third leading cause of death. So this is a big deal. This is important. It's something we have to think about. And we, as and the public agencies need to do a good job of investing public money to do the best we can. As academics, we are hoping to inform that process, that methodology that goes and that has evolved to do the best job, to help people do the best job. So just to give a bit of definition, so we're all on the same page in the starting point, the objective of what I'll call hotspot identification, HSID, that is a hotspot or black spot promise. If you look at the literature, we talk about places that perhaps need to be fixed or improved some way. The objective of that is to identify transportation system locations, and it could be all kinds of different locations, that possess underlying correctable safety problems. So we think there's a deficiency. Caltrans spends enormous sums of money sending groups of engineers around the state of California to look at sites to see if there are problems. So they go first with some analytics and say, these sites might be problematic. Now we're going to send a team to go out to this field, and you're going to have to stay in a hotel for a week while you're out in the rural parts of California and check out the sites and see if there really are problems. So it's an enormous expense, let alone having to do a good job of investing public money. It's also a very expensive activity that the transport agencies undertake. So this is the context under which we do safety management around the world, in the United States, Australia, and other developed countries. First thing that you're probably all aware of, that people that live and work in transport agencies require empirical evidence. So my hunch about something being unsafe is not enough, typically. I might look at a site and say, well, I don't think that's designed well. I don't think that's not going to be enough to justify and make an argument about us doing something. I need hard evidence. So we need some empiricism. We need some analytical support to make decisions of that magnitude. To invest $15 million in an intersection improvement, I better have some hard evidence to do that, right? We also have budget limitations. So we don't have an endless pot of money to invest and make improvements, so that also constrains us. We also have incomplete reporting of what we're trying to solve. And we we essentially have this notion that we want to get rid of the sites that are, or improve the sites that are not performing well. So I'm just going to give you a little bit of an analysis context, because I'm not going to spend any more time on this, but I want to make you aware. To properly assess any methodology by which we say this is how you should figure out where the problem places are, any methodology we would use to understand how well it's working, we would have to use synthetic data. This is an important point, so I want to understand it. But we don't actually know out there which sites are truly bad sites. We're trying to develop a methodology that helps us to understand which ones are truly high-risk sites. So to test a methodology to see if it's working, we actually have to simulate data experimentally to see and test what methods are able to identify truly high-risk sites. Now, I'm not going to talk about that anymore. I'll show you what some data look like, but I won't spend much time talking about that from here on. There's other things. Then the next part is how would we would compare one methodology versus another. Well, let's think that through for a little bit so you can understand. Say I have public money to spend and improve a site. So I go and I say, there's an intersection right over there that I want to spend $10 million on, that I think is a bad site. If I'm wrong, I'll spend $10 million over there erroneously. So I will waste public money and fix the site that actually isn't a bad site. And I think probably in the back of your head you're saying, how could it not be a bad site? Why would you do that? Well, I'll show you how easy it would be to do that. So the other thing I could do wrong would be that there's a site over there that truly is bad, but my methodology didn't identify it. And so I'm not even paying attention to it. I'm not going to spend, or I'm going to fail to spend and invest public money over there and fix something that I should be spending money on. So those are two errors that I would use, or I could calculate, keep track of to identify what methods work better than others. And I would call those false positives, false negatives. And there's a number of other tests that we could do that are talked about in literature that I'm not going to spend any time talking about. But that's how we generally have compared methods over time. And generally, with some exceptions, the methods have performed better over time on these metrics. That is, as we've gotten better with our methods, we identify fewer of those sites where we spend money on them. They're not really bad, and fewer sites that we didn't recognize where we should have spent money. All right, let's get into this. A little bit of an understanding. So for those of you who actually worked in safety, which I'm guessing is a small percentage, what I hope you take away from this presentation are some insights about the thinking that has evolved over time, because it doesn't show up in the literature. We're talking the thinking. If you're not in safety, what I hope you walk away with is a very good understanding of actually how we view safety and think about the problems we have. This is a simulated set of data, and I want you to look at for a second, because it gives you a really good notion of a first glimpse of how challenging this task can be. So what I have down here, hypothetically, are 30 sites. So let's pretend, for argument's sake, they're intersections. 30 different intersections. And I want to know how well they're performing. So the next column is what I call the true Poisson mean. The truth. So this is simulated data, so I've said crashes follow generally a Poisson process. If I sit here and observe the crashes and count the crashes that observe month to month or year to year at a site, that distribution of those crashes will generally be Poisson, approximately Poisson distributed. So I can say, for example, the first site has a Poisson mean of 4, and it's actually among this group of sites, it's the truest, the safest site there is. It has the lowest crash rate, and this one down here has a 2+1 mean of 20, and it is the worst. It is the riskiest site. Are you all with me? That makes sense? So, these are just random number generators. So for example, for this side, I've done a random number generator from a true polynomial of 13. And this is what I might see over years. These are years of observation. That's the variation you would see. This is exactly what we see when we look at crashes at different locations. Now here's the problem. You can see it immediately. Let's look at this site here, site 5. That's at 15. It's only a true polynomial of 10. But it recorded a 15 in that year, and then it dropped down to a 4. So 1 year, if I'm an engineer, I say, wow, 15 crashes in 1 year, that's a problem site. Well, actually, next year we're down to 4. That seems like a safe site. Is it really jumping from hazardous to safe back and forth? We don't think that's the case. We'll get to that in a minute. And if I looked at this, if I only observed this year of data, this one, which is the worst, almost the worst site in the bunch, only recorded 8 by random nature, only recorded 8 accidents in that given observation period, compared to this one that recorded 15. So if I looked at these data just objectively and say which one's the worst, I would conclude that this one is pretty bad. Much safer than that one. Yet, we know truthfully that's not the case. What really happened is that the nature of crash occurrence is such that this had a random down fluctuation, that one had a random up fluctuation. So I better adopt some approach that is able to figure this out. And this illustrates the challenge we have with crash data and trying to make sense of them, or one of them. So, what were the initial assumptions when we started, and this is going back 20 years, started thinking about this problem? I'm going to go through these very quickly. Assumptions are really important because, and especially with safety, but in a lot of your areas you're working in, people make assumptions in the research, and then we forget them. Those assumptions were made, and we've accepted them, and we go, okay, good, those were made, and I'm not going to discuss those anymore. But sometimes those assumptions were pretty bad assumptions to begin with. And I'm going to show you some that we'll come back to at the end that are pretty troubling. So safety is measured by both the occurrence and severity of crashes and their relevant harm. That's how we measure safety. Talk about a dilemma. We have to observe, see crashes, in order for us to figure out how to eliminate them. Talk about a bloody dilemma. Wait, we don't have enough data yet, so let's let the intersection, this crappy or harmful intersection, carry on for a couple more years so we have enough crashes to then say, yeah, we should fix it. I can't fix it now, even though it's a bad site now. I have to wait a couple years before the crashes accrue, and the risk or the safety or unsafety of that intersection reveals itself. That's a fundamental dilemma. How are we going to get over that one? Risk is only comparable across sufficiently similar entities. I don't know if people have heard this expression or this question, and a lot of people have, but is it more risky to fly or drive? And how do you calculate that? Well, the answer to that question is it's irrelevant, actually, because they're totally different things. Flying an airplane, I'm not at 20,000 feet elevation or 40,000 feet elevation. If something goes wrong there, it's a very different proposition than if I'm driving a car and I get a flat tire. Why would they be the same? Why would we expect them to ever be the same? We wouldn't. Why would we expect them to be comparable? We shouldn't. So the same logic applies at the transport system level. We wouldn't expect safety at an intersection to be the same as it would be at a road segment. Because an intersection is a very complex operation. People are going across each other's paths. People have to yield, all that other things. On a road segment, on a limited access freeway, we have very different things. We're merging, diverging, very different things. So we shouldn't compare those. So that's something that has been an assumption from the very beginning. And there are black spots and not black spots. The fact that we have budget limitations means that we're going to group a bunch of sites and say, these are ones that need to be fixed and the rest are okay. But it's not a binary outcome. It's a continuous distribution And we've imposed our own dichotomy there. All right, so let's talk a little bit about the development. This is really a timeline of the development. I'm not going to go through all these. I certainly don't have time, and I'm going to focus on a few things, but this is essentially what's happened over time. We started with very simplistic methods and have gone up to here. We're now beyond here, and I'm going to talk about where we are now, where we need to go. The very first approach was, well, this is a simple problem. We'll just look at the sites and rank them by the most crashes to the least crashes. And so these are actual real data. And it's just a site ID, 1 through 21, and they're the total accidents reported in a 1-year period. These are from rural intersections in Georgia. So the engineers, the academics, 20 years ago said, well, that's a simple problem. We'll just rank order them. And so now I've rank order them, and now I've got the highest 38 crashes recorded in that year, all the way down to 9. From my previous table, you should immediately recognize that that's a real problem, because we don't know if that 38 is a random up fluctuation of something that's much safer, or how all of these perform. So how we need to get around this problem. So that's what they did in the beginning. And we did that in practice for a decade almost. And people said, wait a minute, there's a couple fundamental problems with that. It does not incorporate systematic variation. So that fluctuation we see in crashes, and these things that we see in crashes and incidents on roads are not exclusive to roads. They happen in air travel, they happen in other areas, but I'm focused on the roads. So what we might see in crashes is the blue line from year to year, and these are real data. You see fluctuations. So how can we make any sense out of something that fluctuates so much? Well, we might develop a notion that, well, some underlying unobservable safety or some moving average might better capture this underlying safety of a site. And that would be a better way, perhaps, to try to understand how it should perform compared to how it is performing. So we came in and added a few more assumptions at that point. And we said, safety is not an absolute thing. We just don't need to count the total crashes, but it's a relative thing. So how does a site performing relative to how it should perform? Where we're talking about the notion of should. We also borrowed this notion from epidemiology. We came in and said risk is measured by the number of events divided by some kind of exposure to the events. And so we said, well, let's take into account exposure and looking at risk. Exposure comes from epidemiological studies where people were studying contagious diseases, particularly colds. If I am sneezing and I have a virus, and if you come into contact with me, then your chance of contracting the virus is some positive probability. So if you're an epidemiologist and you want to know what the chances of me getting a cold if I'm healthy, is how many people I come into contact with. Okay, it's fairly straightforward. I can calculate the probability of me getting sick by how much I interact with the population. So when the Ebola outbreak, that's all those epidemiologists do. Who's talking to who, what airplanes are they on, how many people are exposed, et cetera, right? It's all about exposure. So we did the same thing in safety, and somehow we decided that AADT was the best unit of exposure. That the amount of traffic going across a road section is the most important measure of how many vehicles are being exposed to the risk. But it's one of many possible exposure metrics, and it's very complicated. It's much more complicated than the disease contagion problem that epidemiologists face in many respects, because exposure is very complicated. We'll talk a little bit more about that. And we added this assumption that safety is no longer this idea of a measure of how many crashes are recorded at a site, but it's some notion of an unobserved or latent construct or property of a site. And the last thing is that we say crashes arise from a single underlying data generating process. And I'll talk to you about, show you what that means in a second. So I hope you realize now random fluctuations in crashes can make you lead to bad decisions if you chase the actual number of crashes around. So the profession then said, well, we need some notion of expected. How is a site expected to perform? And so we came up with these notions of safety performance functions. And they're all over the literature. If you look over the last 20 years of literature, there are probably 1,000 journal papers on safety performance functions. Just so many. Far more than we need. But the central idea is that we can predict what the expected performance of a site would be by looking at the length. So for a segment, the length of the site, the volume of traffic, so this is counting for exposure, and a number of attributes of the site. So I want lane width and median width and configuration of a segment, speed limit, all things like that. The notion is then, if we have a good notion of expected, if I have, now let's go back to my hypothetical example. If I have 20 intersections that I'm supposed to manage, and I can develop a model that says, here's how the intersections are expected to perform. I have a lot of intersections. I do a model, and I can predict how they should perform. That is the mean performance, given that it's got speed limits of X and lane travel widths of Y, et cetera, et cetera. I can then look at the observed minus the expected. How many crashes did occur there versus how many did I expect to see there? And the larger the difference, the more outlying it would be, and we would then call that a hotspot. So that's an improvement of the simple ranking. That's going to help us to now understand hotspots. Here's an example of what the data, and you might all guess, the data sets look like. Now we've added some more variables, median height, median width, et cetera, so we can develop these models. We can test the statistical significance of all these things and influencing the crash count to come up with a predicted value. Here is one example from one of my papers that I pulled out. This was this is a single equation of picking the count of crashes that includes horizontal curvature and the curve radius and the ADT, the heavy vehicle ADT, et cetera, right? So all these things were important in predicting the expected performance. And then I could then look at the observed count, take that difference and say, okay, this is doing a better job. It still, though, suffers and it doesn't account for regression to the mean. How many people have heard about regression to the mean? Okay. If you haven't, you're in for a treat, because regression to the mean is really cool. And I'll tell you, if you understand it, if you understand that one thing leading today, you will understand a lot more than most, because most people are very confused about what regression to the mean actually means. So I'm going to explain it to you. But so far we haven't dealt with it. But it's a real problem, and I'll explain it to you. Suppose you know a mother and father. Okay, you know some couple where the mother is 6 foot tall and the father is 6 foot 5 inches tall. All right? Imagine that in your mind. My question to you, what is the probability that their natural-born son is taller than 6 foot 5? My other question to you is, what is the probability that their natural-born daughter is taller than 6 foot? In other words, what's the probability that the son is taller than the father and that the daughter is taller than the mother? Does it seem like it would be, as a statistician, 50-50? Does anyone want to go 50-50? Why wouldn't it be 50-50? Okay, everyone's very nervous about saying anything. Because it seems like a trick question, and it kind of is.
I still get better nutrition from generation to generation, so we should be taller.
Well, we do get better nutrition from generation to generation. If it was, let me say it this way, if it was 50-50, the human species would be getting taller and taller and taller and shorter and shorter and shorter. But that's not happening. We would have, well, I would have to calculate the time. We'd have 15-foot people walking around. It can't be 50-50. The reason it's not 50-50 is because this mother and this father are taller than the average people in the population. So regression to the mean is a phenomenon by which when you pick something that is outlying in the population, its, in this case, offspring are more likely to regress to the population mean in height than they are to be taller. So the probability of them being taller is much less than 50%. I don't know what those exact probabilities are. The taller they are, the lesser that probability would be. Why does this even relate to road safety? Well, it relates to road safety because what we do in road safety, and the practice has been, is that we go out, we collect all this information about sites and how they behave, and we say, oh, these are all the ones reporting high numbers of crashes. They're not average at all. They're the top. They're the tall fathers and the tall mothers. And we pick them and say, okay, so let's take those and let's look at them. And now, if I'm not too savvy of an engineer, I say, well, I'm going to go fix all those. And I'm going to look at them next year and see how well I did as an engineer. Guess what? Without any engineering know-how, it will look like I did a great thing. Because by statistics alone, next year, the crashes will go down. Because they were all picked above average. So regression to the mean is an artifact that arises from non-random sampling. And it's not only non-random, but it's systematic bias sampling of a segment of a population that's outlined with respect to something you're interested in. And all the things we've done so far have not accounted for that. So a pioneer named Ezra Hauer came along and introduced this empirical Bayes correction, which corrects for the fact that things are outlying. And so what we do, and what this correction essentially does, is says, well, if the more outlying it is, the more I would expect the next observation period to be lower. And so if it recorded 10 this year, I would expect only 8 next year. And then I'll see what happens next year, because it's outlying or suffers from regression to the mean. And so this correction was done, and this is now close to current day state of the practice. And I won't go through this equation, but this is the regression. It's a weighted average between the expected, it's the safety performance function, and how all the sites perform, and the actual count of crashes at the site. It still doesn't account for the single equation problem. And this is something I've been working on over the last couple of years. And this is a limitation. So everything we've done so far assumes that there's a single equation that can predict how many crashes occur at a site. If you think about an intersection again, what do we all know about the causes of crashes? Again, the statistics go around in transportation. What's the number one cause of crashes? So, okay, so you're getting very specific. You're right. So speeding is caused a lot. It's human behavioral problems, right? So the engineers that design the roads have some culpability, but mostly it's the human errors that account for most. So the problem that we've been trying to solve is, well, we might not have just one process going on, but 3. Or it could be more than 3, but we propose 3. That we have a process that there's some factors that determine how many human errors there would be at a site. There are factors that determine the geometric operational errors at a site. And there might be factors that determine unobserved spatial effects at a site. Crashes caused by animals running onto the road, or glare popping up. That have nothing to do with the geometry and geometrics, have nothing to do with human behavior, but they have some spatial artifact that arises. So we've been developing a methodology to develop 3 equations instead of one, to try to capture the fact that there could be multiple processes generating crashes at a single site. All right, so that brings us to current day. There's still this dilemma that is really troubling to me and to a number of other people and other academics, and that is this dilemma that we have to wait for crashes to occur before we can actually figure out what to do with them and go fix the sites. We call this the reactive method of dealing with safety, right? The problem is, and the problem has been, that if we take a proactive approach and say, well, let's try to actually fix things earlier in the game, let's not have to wait for crashes to occur. Until now, we haven't really had a way to do that very rigorously with strong analytics. Most of the proactive methods we use and right now are very subjective. Engineers going out to site and saying, yeah, that looks good. It meets all the conditions. I think it's fine. But a lot of people that want to invest millions of dollars aren't okay with just a group of engineers saying, talking together and saying, yes, I think that's a good site or a bad site. They want hard evidence, especially when they're called to the mat from the public and spending large sums of money. This is a problem. So, where do I think where we're going and where we're going to try to address this problem? And I think this is actually very, 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 very cool. I think we're headed in a very different direction than safety, and we will be, and we'll be seeing this going forward. We're going to be using and developing much more in the way of surrogate measures of safety. So instead of waiting for crashes and looking at crashes to figure out when things are not safe, we're going to be looking at different metrics. And we can do it now with all the technology. So I'm just going to give you one example. This is a time to collision diagram. And what I'm showing here are 2 vehicles, 1 and 2, on a trajectory to hit each other. They're going on a velocity and a direction that they will collide unless one of them changes direction. I could say, for example, knowing this velocity and that velocity, I can say, okay, there are 4 seconds before these 2 vehicles will collide. And then they keep going toward each other, and I go, now we're down to 3 seconds. And then one of them diverts. This one notices that one and either brakes, so they're no longer in a trajectory, or turns, or veers, or whatever. And we could say they got within 3 seconds of hitting each other before one of them diverted. Right? Does that make sense? And I have 2 different examples. There are 2 vehicles following each other, and these would be their head-on. If I could figure that out and calculate it, then I might be able to do a better job of understanding that. So we just finished a study of a fairly complex intersection in Brisbane. And this is actually a fairly new intersection. And you can see the number of legs coming into this intersection, how complicated it is, and the turning, and the fact that it's a skew intersection, and it's all kinds of things going on. We have a whole bunch of pedestrians. We have a major bike thoroughfare through here. We have pedestrians here and here, and riding through here. And so very, very complicated. From a safety perspective, how do we understand what's going on there? What do we do? What we're doing now, we've put a bunch of intersection cameras at this site. And there's technology available now where we can track things. So this is technology developed by Tarek Syed in University of British Columbia. He's been developing this technology for about 12 years now. And what this technology does is, and it's only showing you a couple things, but it identifies, automatically identifies every single pair of whether it's 2 pedestrians or pedestrian and a cyclist, a vehicle and a pedestrian, et cetera, every single pair that are on a collision course, and calculates precisely how close they are to getting to each other before they hit. And you can develop a distribution of time to collision. So we're starting to get to the point now where we can think about safety. Here's another clip. Now, it does it for every single thing on there, but it's just showing you. So that it can calculate how close these got together, the deceleration rates. The technology is so good, it's actually quite mind-blowing. If you put these cameras on, and this is all automated, you just put it in and it spits this out. It can tell if cyclists are wearing helmets or not, 90% accuracy. It can tell if a pedestrian is a male or female with 90% accuracy without any input from a human. It can distinguish between heavy trucks and vehicles and pedestrians and bicyclists. And it does it all for the entire intersection of every single pair that's on it. So we can start to think about monitoring and developing a distribution, if you will, of time to collision. So how many vehicles came really close to each other. So these are the number of vehicles that came in within, or pedestrians, cyclists, that came within 1 second of collision before one of them avoided the collision. One of them slowed down or stopped. As you can imagine, now the basis of this is that at the top of this pyramid, so we have all the activity that happens in the road network. Very top of the pyramid, the smallest fraction are fatal crashes. These are the worst outcome events. Just below those, on a much greater number, are injury crashes. And just below those are property damage crashes. They're not as severe. And just below those, if you take that, so this is all driving, and very little of all driving results in crashes. But this next area here are these conflicts. So these conflicts are as precursors to crash. So the real research, I think, over the next decade, probably the next decade, in safety is to get away from this reactive, let's wait for crashes to occur, but let's now focus on how do we develop relationships between these serious conflicts or conflicts that we can measure and crashes. Are the relationships different by accident type? It probably would be. Are they different for different transport system locations? Freeways versus intersections, etc. How do those relationships play out? And so I'm working with Tarek Syed to do some of that work. We're doing it in Brisbane now. I just met with the transport agency in Brisbane, and they saw this, and I went through a much more detailed report of 3 intersections, and they said they'd never seen anything that was so drastically, it had such drastic potential to change the way they look at safety in their business as this technology. And now they're looking at putting cameras in a bunch of places because they suddenly have a way to measure. This satisfies that metric that we need a lot of analytical support to do rigorous analytics without having to wait for crashes, which is horrible for everyone in that dilemma. So that's what I had to share for you. That's sort of a history of where we've been and the thinking, and just sort of a glimpse of the thinking and the evolution of thought. There's a lot of devil in the details, as I say, but there's a very rich literature that describes that journey. But that is the journey that's really transpired in the transport safety sector, at least on the road transport side, and the thinking that's gone along the way. And some of the assumptions that we started with in the beginning are really problematic. And those are the ones that we, as academics, I think we have to question. We have to say, how do we get around some of these assumptions? And we chased reactive safety for for 3 decades, forgetting that there's this built-in dilemma. We're having to let people die before we actually figure out how to safety, which is really, really tough place to be. Hopefully we're on the right road now, and pun intended. And we can make some progress to try to understand and do a much better job of doing safety in a proactive way, and not have all this stuff happen. Now, the last thing I'll say is everything's up in the air with driverless cars, and and how that unfolds. I have my own thoughts. I purposely didn't put that in here, but the whole driverless technology and the impact on safety is a whole new area that can change a lot and will change a lot, and it's something that a lot of people are thinking about as well. So anyway, thank you very much.